Welcome to the second video in this chapter, and in this video I will talk about that displacement measuring balancing machine. You can see that there's just a slight modification at the two bearings. In one of the direction here there is a displacement possible and there's a spring included in order to limit, of course, also the motion, so to create some kind of restoring motion there, and then to be able to measure and to relate these displacements to forces. So this is now a system that has 2 degrees of freedom. So there's, of course, a third one, the rotational degree of freedom, but there is one degree of freedom that is related to each motion on the left and of the right hand side. I could say they act independently, but I could also represent them, of course, by one rotation around the vertical axis here and one linear displacement. So it's a 2 degree of freedom system if we consider that rotor in stationary state, and the derivation of the equations of motion is quite involved. So this is a nice exercise in order to repeat Lagrange's equation of second kind for this system. So Lagrange's equation of second kind, you will find them here, are obtained for the difference of the kinetic minus the potential energy. You can see the kinetic the L here inside that equation. You take the derivative with respect to the generalized velocities here to the generalized coordinates, and for the first term you have to take the time derivative. On the right hand side, you know from your course in engineering mechanics, there should be a Q which represents the generalized forces of the non-conservative force, or related to the non-conservative forces or effects here. There are no non-conservative forces that we consider here. So we do not consider any damping or dissipation effect here. Yeah? So therefore on the right hand side there is the 0 here. For the 2 degrees of freedom, or for our generalized coordinates q sub 1 and q sub 2, we have the choice. We can choose x sub 1 and x sub 2, which is quite obvious here. And we can also choose, as I said at the beginning, some linear displacement and some rotation here. The situation is shown here. Let's have a look at that plan in the middle, where you can find the center of gravity. That plan in the middle, also approximately in the middle, where you can find the center of gravity of that rotor, is displaced by some amount x. And then there's a rotation of the true axis of that rotor here by some angle psi. So instead of x sub 1 and x sub 2, I could use the displacement here in the plane of the center of gravity and the angle psi. And of course, if you look at kinetic energy and so on, this setting makes more sense than using x sub 1 and x sub 2. So be very, very careful at the beginning, where you make your choice for these generalized coordinates, not to choose something that is quite obvious, perhaps, from the system, from the design, but think about the physical quantities that are involved and that you want to make visible inside the Lagrange's equation of second kind, and where you have to take the derivatives. It could lead to much more work here if you choose the wrong, or if you choose wrongly, your generalized coordinates. Okay, now this being said, let me start with the part of L that is the most simple to treat. And this is for sure the potential energy. As you will see, the kinetic energy is a real lengthy derivation. So let's start with the potential energy. The potential energy will come from the 2 springs, left and right. So it's quite clear that the potential of a spring is half c x squared, where x relates to the displacement or elongation of the spring. So we take spring constant c sub 1 relating to bearing 1, spring constant c sub 2 relating to bearing 2, and the displacements are denoted by x sub 1 squared and x sub 2 squared. So here you see, here you have these obvious displacements, x sub 1 and x sub 2. But believe me, it's much more easier to switch here to x and psi than to do the opposite for the kinetic energy. The kinetic energy is really, really quite involved. So we replace x1 by x minus then that difference here, which is L sub 1 times the tangent of that angle, and then you obtain that distance here, and you take it with a negative sign as the positive sense for psi is shown in that figure. Well, the same can be done for x2. You start with the displacement x here in the middle, and then you have the angle psi. So you add some additional displacement here relating to the difference between O prime and x2, and this is just L2, and then you take the tangent of this angle here, L2 tangent psi. You see there's some space in between these equations here because we want to linearize the equations and make life a little bit easier. So we want to avoid that nonlinear quantity, the tangent of psi here. And there are good reasons to do this because usually the motion is limited in these bearings, so there won't be large angles possible for psi. So we have x minus L1 psi if we replace the tangent of psi by its argument, and same for x2, we have x plus L2 psi. Well, and now we can build our potential energy, so we just have to take the square of these expressions, so leading to a term in x squared, which is c1 divided by 2 plus c2 divided by 2 coming from x2. We have another term in psi squared, so let's start with the last term in the expansion of psi squared. We have psi1 times L1 squared divided by 2 plus psi2 times L2 divided by L2 squared divided by 2. So this is the term in psi squared. And then we have a mixed term, and now you see the difference in sign here and there. So we have C1 times L1 with a negative sign, and this has to be multiplied by x and psi. And now if you ask yourself where is the 2, this term has to be taken 2 times according to the classical binomial formula. And the same here with the term C2, so with the second term here. The mixed term would be the product of x and psi times L2, and again you have to multiply by a 2, so this 2 goes away, and you have 2 times, you have C2 times L2 times x psi here. So this is the potential energy. We know that we have to take the derivatives of the potential energy with respect to x and psi, our two generalized coordinates, in order to have the contribution for the Lagrange equation of second kind already for the potential energy. So let's take these partial derivatives. It's not difficult. Derivative with respect to x comes from the first term and is then c1 plus c2 times x. And from the last term, from the mixed term, it's C2L2 minus C1L1 multiplied by psi. Already here you can see that the equation of motion that we will obtain will be coupled, because this is the contribution that should matter for the, well, if we sort them first and second Lagrange equation that we will obtain 2. That would be the Lagrange equation that governs x. And you see that in that equation that governs x, that psi appears from that mixed term here. Yeah? So again, that rotation relates the two terms, or couples the two equations of motion, a very classical result in dynamics. So next, we take the derivative of the potential energy with respect to our angle psi. So what we have is, we look at the second term, the derivative of the first term being 0. We have C1a sub 1 squared plus C2a sub 2 squared times psi. And finally, we have from the mixed term C sub 2a sub 2 minus C sub 1a sub 1 x. Okay. And as I said, this was the part that is easier than that comes now. Now we look at the kinetic energy. I start here with the definition of the kinetic energy. For every material point, you have to determine the velocity. So you compute the velocity field. And from the velocity field, you integrate over all material points. You get from the square of the velocity field, you finally get, by multiplying with a mass element dm, you get, and integrate, you get the kinetic energy. Now, as we are dealing here with a rigid body, still with a rigid body, our rotor, we can represent the velocity field by the velocity of one particular point, which is chosen here, guess what, O prime, the moved, well, center, the center that we used here, O, it is not the center of gravity, it's the origin of our coordinate system that is now just moved by the fact that we have the flexibility at both ends, so at both bearings here, to point O prime. So we take the velocity state in that point O prime, and then we add some omega with, where we take the cross product with R. So in order to be brief, I represent this by VU prime plus the relative velocity with respect to that O prime reference system. Now let's do the integration. So plug in that result here for V and then do the integration. You will get 3 terms by multiplying the 2 vectors V. Yeah? So it's a classical binomial formula. The first one is the product of VO prime by itself. The second one will be the product of VO prime, so first term, it's a mixed term, by omega vector product with R. The last term is written perhaps a little bit strange way here because it's the same term, omega vector product of R and VRL. It should guide you a little bit, I would say, through the fact that we can move here because we have what is called in German a Spartprodukt. We have a product involving a vector product and a scalar product, and we can change the order of the terms in that product if we do not do any permutation here, so clockwise, permute only. If we permute counterclockwise, of course, we would just change the sign of this term here, but this is not intended. Okay, let me call these 3 integrals T1, T sub 2, and T sub 3 in order to study them separately. Of course, on the next slide, because this one is already overfull, I would say. So let me summarize the results. This is the term for the kinetic energy by just making use of the classical formula of the velocity field for a rigid body and relating it to the velocity of the point O prime, the shifted origin of our coordinate system. So for T sub 1, things are very simple. Everything is a constant here, so independent on space, because we are just considering one point, namely the point O prime here. So we just have half the mass of the rotor, which is denoted by a capital M, and then we multiply by the norm squared. So the scalar product of a vector by itself yields the Euclidean norm squared. Well, and that's it. The Euclidean norm squared of the velocity of at O prime. For the second term, we also can simplify that equation because VO prime and also omega are independent on space, on the spatial coordinates. The only thing that depends on space is that R is the position vector starting from O. Well, you know that, well, then you can integrate over R dv, and you know that the result from integrating over R dv is just the information where is the position vector to the center of gravity, that should be known, and multiplied by the mass m then. a classical result that you obtained when you studied the static mass moment. And for the last term, well, things are a little bit more involved. The last term represents, if we shift the dot to the first entry, it represents, so if you circle these terms here, yes, or cycle these terms, it represents half times omega, the rotational speed, as a dot product with the angular momentum, referring of course to point O prime here, or that's just represented by a prime, and the O has been left away for simplicity reasons. Okay, and A prime can be represented by the mass moment of inertia, now also related to point O prime. But O prime is just the shifted origin. So the whole rotor is shifted to that point. No problem with that. So these are the representations. But now we have to insert expressions here. And we have to find expressions for VO prime, for omega, taking into account all the rotations in the system, not only the rotation around the axis of rotation of the rotor, but we also have our rotation with psi, right? And, well, yeah, and also for J prime, but this is not a big deal. No? Okay, so let's do this. So I transferred the results for the three integrals, t sub 1 and t sub 2 and t sub 3, to the next slide. I just show you again the situation here. What's very important is now that new axis of rotation compared to the theoretical axis or the axis at rest, and our coordinate system where the origin has moved to O prime and where we have the angle psi, inclination angle psi. So what can be said about VO prime? Well, VO prime, it's the velocity of that point O prime. And now you see the reason why it makes sense to introduce that distance here. Because, well, it's quite easy to compute that velocity. It's VO prime is equal to x prime ex. If we denote by ex now the unit vector pointing from O to O prime, x dot ex. For omega we have to take into account two rotation angles. So we take the angular velocities with respect to these two angles. The first one is with respect to the vertical axis, E sub y, it's minus psi dot. If you look at the definition of the axis and of the, so would point upwards, so positive direction would be like this. And our angle psi was just in the opposite direction, so therefore the negative sign. And plus omega and the rotation about now one body fixed axis E zeta. And finally we also have R sub s. And R sub s, center of gravity, is always aligned with the eta axis. So it's the body fixed axis in the radial direction on which the center of gravity is located. And finally we have J prime, and J prime is our classical mass moment of inertia tensor related now to the body fixed coordinate system that starts now in O prime. O is just one theoretical axis. The whole rotor has moved to O prime, and this is then the starting point for our body fixed coordinates. If you look at this situation, then you will say with me that this is really a mess. You have some unit vectors referring E sub x and E sub y to some space fixed axis, a horizontal axis in which we displace the rotor or allow him to displace in the bearings, and a vertical axis where no displacement is possible and where the rotor rotates around, so shifted around due to the rotation in the possible rotation in the bearings, and or displacement in the bearings here. And then we have still body fixed coordinates, of course, for J prime and for R sub s. And for omega, we have a mixture of both. Terrible. So we have to transform variables to another coordinate system in order to be able to do the computations, in order to determine the scalar, finally, independent quantities of any vectors t sub 1, t sub 2, and t sub 3. But in order to carry out the algebraic operations here, the coordinate systems, the unit vectors must be the same. Otherwise, it would be very dangerous and leading to an error to carry out these operations of dot products and vector products. So, and in this respect, it makes sense to transform E sub x and E sub y. They are in minority, I would say here, compared to all the other places. Think of J prime alone, yeah? Of the other places where you find the body fixed coordinates. So we transform the space fixed coordinates to co-rotational coordinates. Yeah? And this is done on the next slide. So, two coordinate transformations. The first one is with respect to psi, and the second one is with respect to the rotation of the rotor, so with respect to the product of omega and t. Let's consider the first rotation. It's around the space-fixed vertical axis, I would call it the y-axis, and by an amount of psi. So as you can see from that figure here, if you want to compare, if you want to compute the vectors Ex and Ey, you might ask, why is there no Ez here? Because, well, let's say we don't need it anymore. No? So we just consider E sub x and E sub y. We said we want to replace E sub x and E sub y, our space-fixed unit vectors, and relate them to the co-rotational body-fixed unit vectors, so we don't need any Ez here. No? So that simplifies things, because for E sub y, and the thing is quite clear, E sub y is E sub y prime. E sub x, well, has to be related to the projections of Ex prime and Ez prime. So we have Ex prime, which is then projected by a cosine function on Ex, and we have Ez prime, which is projected by the negative of the sine function on the axis x, and therefore we get this result. Finally, we express or relate these prime coordinates Ex prime, Ey prime, and also Ez prime to the body fixed coordinates by rotating again, and now by the rotation, or by taking the rotation of the rotor into account, so by an amount of phi equal omega times t. We rotate this time around the z prime axis, which is then the zeta axis already, the axis of rotation. So then what we obtain after that rotation is our body fixed coordinates psi and eta. Here are shown the intermediate coordinates y prime and x prime. And well, then you do the classical computation. So for Ex prime, you will find a contribution from the psi axis by a cosine projection, cosine omega t. And for E eta, you see that you get a sine projection here, and it's opposite to the x prime axis, so you get minus sine omega t E eta. For E sub y prime, so for this axis here, you do the same. You see that you get a cosine contribution from eta, and you get the sine contribution, and this times with a positive sign, from E zeta. And finally, the z prime axis remains unchanged during that rotation. It's the E zeta axis. Now plugging in the results for Ex prime and Ey prime into, well, the first equations, you see that you can express E sub x and E sub y by finally E sub x, E sub psi, E sub eta, and well, also E sub zeta will be present here in the first equation. So this is done on the next slide. You see the final result, technical result for E sub x and E sub y. And I also save all the results we computed and discussed before for VO prime, omega, and finally for RS and J prime. And now let's do the computations. Let's start with T1. What was the expression for T sub 1? Well, basically we have to compute the norm of the unit vector of the vector O prime. The good thing is that the norm of that vector can be computed in any coordinate system because the norm of the unit vector amounts just to 1. So no necessity here to transform anything. Yeah. You just have half mass norm squared of vector VO prime, and this is clearly 1/2 mx prime squared. For the next candidate, things are more involved. For T sub 2, we have the product of VO prime times omega, which is then taken in the vector product with R sub s. Now we express a VO prime in body fixed coordinates. So we replace the EX by cosine psi cosine omega t in the first member, by minus cosine psi sine omega t in the second member, and by minus sine psi in the third entry here. We take the dot product with the expression omega vector product with Rs. For omega, we have one part that we do not have to transform. Where is it? Omega here. Omega Ez. Zeta is the last entry. However, the first entry with Y has to be transformed to the co-rotational coordinates. So therefore, we have sine omega t minus psi dot, first entry, and minus psi dot cosine omega t for the second entry. And we multiply with our nice vector Rs, because it's just O, E, O. Having all these computations done, which is now just technical to evaluate these two products, we arrive at the following expression, mx prime sine psi E psi dot sine omega t minus cosine psi E omega cosine omega t. Now this expression is clearly nonlinear in the coordinate psi, and there's also a nonlinearity with respect to that x dot here. How can we save that situation? Well, we can linearize here the kinetic energy in order to arrive at the very end at linear equations of motion. So we start to linearize as soon as possible, and what we do is we of course observe that the angle psi is small. Then we can replace the cosine psi just by 1, and we have a first term here where we have sine psi, which we would replace by psi, and which is then multiplied also by psi dot, from which we assume that this term is negligible with respect to the other term here, where we have just E omega and cosine omega t. That will be much, much larger than multiplying it with that tiny little psi here. Yeah? Okay, so we linearize that term by just taking the second one into account and by replacing the cosine psi by 1, and then we have minus mx dot E omega cosine omega and t. Well, there is not much space for the third term here, so let's just consider these two terms, these two parts of the kinetic energy, and compute already for these terms. They are quite small. The other one will be much more involved. Compute the partial derivatives on the next slide. So these were my two terms. The partial derivative of each of these terms can now be taken with respect to x dot. And well, there is no other influence here because we linearized the mixed term. So the influence on psi goes then away. And for the third contribution to the kinetic energy, we will have a contribution with respect to psi dot. So this is the only part from the kinetic energy which matters for the first equation of motion, the equation of motion related to our generalized coordinate x. So taking the derivative with respect to x dot is just from the first term mx dot here, and from the second term it's just minus me omega cosine omega t. Just copy that term and drop the x dot. And then we have to take the derivative with respect to time of that expression, and this is just the acceleration here. You can see it's the acceleration which relates to the linear momentum or the time derivative of the linear momentum mx double dot plus me omega squared sine omega t. And also this expression is well known to you. It represents some kind of excitation by an imbalance, and that imbalance is present because we did not yet balanced our rotor, so there is the E here. Okay, let's move to the first equation of motion that can now be written. Don't forget, there is the T3 still missing, but that affects the second equation of motion. So for the moment, let's look at the first equation of motion. It is composed by the partial derivative of the kinetic energy, or the two parts we already treated with respect to x dot, and then you take d by dt, and well, it should be negative, but then as the kinetic energy is negative in L, the potential energy is negative in L, or negatively taken into account in L, there's a change of the sign here, plus dv by dx. I recall the partial derivatives. They were mx double dot plus me omega squared sine omega t. And for the potential energy, we had c1 plus c2x plus c2L2 minus c1L1 psi. And now this can be assembled to yield the equation of motion. And you can see that that equation of motion is now composed by an inertia part. Then there would be a classical spring stiffness part. Unfortunately, there's also a coupling term because, well, of the two springs that couple the motion here, C1L1, C2L2 minus C1L1. And you can see that there is an excitation present, at least if there is some kind of static imbalance here. And with this, let's move to T3 and to the second equation of motion. And then I will represent both equations of motion. And I can promise you already here that the second one will be much more longer than that nicely first equation of motion. Again, the rotational motion is much more difficult to describe. Omega is needed here and J prime in order to derive an expression for T sub 3. Well, J prime is classically represented in our co-rotational coordinates. For omega, we have to represent part of that, the first entry here, by E sub y. E sub x is not needed anymore. No? It's just repeated here, not needed in the derivations. So we plug in for the vector omega, we plug in E sub y, we get minus psi dot sine omega t minus psi dot cosine omega t, and omega as before, nothing changes here. We have it here, we have the dot product, we have our j here, we have another dot product, and we just have again omega. We carry out all these dot products here. Very technical. What you can see is, well, you can see it from the last end here already, this is the contribution that matters for the rotation of the rotor, j zeta omega squared divided by 2. Then we have some kind of interesting terms with respect to psi dot squared. Namely, they are related to the mass moment of inertia, those that are on the diagonal, their difference, so to non-symmetry, and there is a multiplication by cosine 2 omega t, which should alert you a little bit here, because it appears in the coefficients, so these coefficients become now time dependent, and there is now a contribution from j psi eta, so from one of the off-diagonal elements, also with the sine function here. And in the mixed term, I could say mixed term omega psi dot, but we will consider the stationary state only, so it's a contribution in psi dot here. You will find also time-dependent coefficient also in these off-diagonal terms. Yeah? So they lead these off-diagonal terms, and that's for this reason I do all these computations in order to show this to you. They lead here to time-dependent coefficients, and you can be sure that you will find these time-dependent coefficients then also in the equations of motion, namely in inertia terms, because kinetic energy relates to inertia effects. So this is my kinetic energy just copied from the previous slide. Now we have to take all the partial derivatives, and they are long and they are technical to obtain and they are not difficult to obtain. So I would just show them here on that slide. The first one is with respect to psi dot. So what you do is, of course, you lose the first term. It does not matter for our equation of motion because it's important just for the rotation of the rotor. And for the first term, you just copy the whole parenthesis here, and you take the derivative of the psi dot here, which is then just psi dot by itself. Psi dot squared divided by 2. And for the last term, you also copy the coefficients, and then you multiply by omega because you take the derivative with respect to psi dot, and that second term is linear in psi dot. Yes, but now you have to take the derivative with respect to time. I'm sorry for that, but we have to do it. So we have to take the derivative with respect to time of these cosine and sine functions here, which are trailing everywhere around, of psi dot. The good story is only we don't have to take anything account with respect to omega because we are considering the stationary state only. Yeah? But the expression becomes even more lengthier. So we have the second derivative here with respect to psi. We copy the whole expression, the whole term in that parenthesis, and then we move to the derivatives with respect to these cosine and sine terms. And well, you can see that you just have to switch the cosine to a sine, and here's a sine to a cosine function. Take, of course, the sine, so the sine of that expression, negative sign, correctly into account, and then it's omega psi dot. And for the last term, you also take the derivative of the sine and of the cosine function. It's then a cosine, the sine minus cosine, so therefore the negative sign still minus sign here, therefore the negative sign here included. And then it's omega squared from the inner derivative. Okay, this is the contribution to the equations of equation of motion, to the second equation of motion, that equation of motion that governs psi. And now we need to add the potential energy. Perhaps before we do this, we have a closer look on that first part of the equation of motion, and you can see it's terrible, right? It has time dependence in the coefficient of the second derivative. It has time dependence in the first order terms in psi. Well, and of course we also have some terms that are independent and they will act on psi, and that will act as an excitation. And you can see that this kind of excitation is a harmonic excitation. So there, I would say nothing so special here. And these coefficients stem from the fact that you have a dynamic imbalance. Without dynamic imbalance, there wouldn't be, at least for this contribution here, there wouldn't be any excitation in that equation. Okay, let's add now dV by d psi. I recall the results. The first result was obtained on the last slide, on the previous slide. And finally, we have dV by d psi. And I copied here the result for dV by d psi. And now we assemble everything to the equations of motion. So we start with the second order term, we then take the first order term, we take the term in psi and we take the term in x, and on the right hand side, so appearing with a positive sign here, will appear this excitation. Yeah? That's it. Okay, so this is the second equation of motion. And as I said, that second equation of motion looks terrible. Now I would like to join here the first equation of motion on one slide, and then we will discuss the result. What can be concluded from these equations, other than they are long. So these are the two equations of motion. What we can see is that these are forced vibrations that occur here, because we have second order equation, linear second order equations. So the good thing, they are still linear because we linearized them. second order equations. And the excitation is a classical excitation here with omega squared. So this would be from classical excitation from an imbalance, so mass force excitation. This is perhaps new, but follows, I would say, the same line. It's harmonic excitation, and it's related to omega squared. So the first thing that can be said, we deal with forced vibration if an imbalance is present. So if a static imbalance is present, then there is a forced excitation in the first equation. If a dynamic imbalance is present, we have forced vibrations for the second equation. So there's the excitation in the second equation. Well, if symmetry, so G eta is not equal to G psi, is not present, so it's violated even a little bit, then we have here a time-dependent term. If J xi eta is non-zero, we also have a time-dependent term. Same holds for this equation here, or for this contribution. So we have possible time-dependent coefficients here. These time-dependent coefficients are periodic coefficients due to the fact that these are harmonic functions, the cosine and sine functions. And this is called a parameter excitation. So this is the point, or the reason why I studied the system in more detail. The first one, it relates to a practical case, namely to measuring displacements in these balancing machines. But you could have these displacements also for the rotor itself, because you do not have perfectly rigid bearings. You will also have some kind of flexibility in the bearings, allowing the rotor to, of course, with small angles psi, to do this rotational and linear motion that is described by these equations. And you see this can create some other excitations, namely parameter excitations here. So the parameters change with time, and that's dangerous. That can be studied. The stability of these systems can be studied. It's beyond the scope of this course. It will usually be done in courses either on vibration theory, especially on nonlinear vibration theory also, then time excitation is always treated, usually. So either in courses on stability theory or in courses on vibration theory, you will get some more details on parameter excitations. What I would like to just present you as a result is that there is additional chance of resonance or possibility of resonance here, namely parameter resonance of first kind, which is called the main resonance. And you can see that this resonance does not occur just only once because of the fact that such a sine function always leads to the same values if you take, if omega 1 and omega 2 are the natural frequencies of your rotor system. If you, for these 2 degrees of freedom, if you take multiples where p is the natural number of these values, so 2 omega 1 is 2 times pi, the natural number times omega, then due to that periodicity, you obtain not only one parameter resonance of that kind, main resonance, called main resonance, but you get countably infinitely many of these. So again, due to the fact that there's a natural number in here. You get twice that family because you have 2 natural frequencies, omega 1 and omega 2, for this 2 degree of freedom system. And there is another effect, the parameter resonance of second kind, where you take combinations due to the additivity of, or to the, no, not additivity, to the addition theorems for sine and cosine functions. You take also combinations of omega 1, or you have to take combinations of omega 1 and omega 2 into account. Sounds terrible, right? So many new resonances. But as before, for the Jeffcoat rotor, the most dangerous resonance is always the first resonance, so the resonance that you would obtain for p equal to 1. So in this case, you have omega equal to omega 1, omega equal to omega 2. Well, this is not a new result. I would say this is the classical result. Avoid the natural frequencies. There are no good candidates for rotational speeds. And then there is a result that we also have seen, omega 1 plus omega 2 divided by 2, which would be something, well, for the Jeffcott rotor at least. So analogously to the Jeffcott rotor, we call it a half critical. Just omega 1 plus omega 2 divided by 2, would call this here. It's not correct because for the Jeffcott rotor, omega 1 and omega 2 were very close together. They're just the effect of non-circularity. Here, of course, it's a 2-degree of freedom system. You could have omega 1 and omega 2 that are quite different. But also, it makes sense to add, if you have two natural frequencies, just to add them and divide them by 2. And don't try to operate the rotor in this range for omega, for the rotational speed. That can be learned from this example. So if you consider the system as a 2-degree of freedom system, determine the 2 natural frequencies and avoid not only omega 1 and omega 2, but also the sum of omega 1 and omega 2, which you divide by 2. So you could say it's the arithmetic mean of these 2 natural frequencies. That's always dangerous, and you will see it if you do the classical waterfall plots. Yeah, and well, this ends the discussion of these equations of motion. I will not undergo the task to solve them, just show them. It was a repetition, first of all, of Lagrange's equation of second kind. It should show to you that even if you consider such a little thing like a flexibility in the bearings, you arrive at a very involved computations, and that you get a new phenomenon, which is parameter excitation, and you should therefore take care of that phenomenon in practice and also avoid the arithmetic mean or half arithmetic mean of natural frequencies. Now there remains one question. How do we balance a rotor? So how do we determine the forces at the bearings, the forces that are needed to counteract these bearing forces, so these forces that we need in the balancing plane in order to add there some mass points and in order to balance the bearing forces by the centrifugal forces of these mass points. So the first example I would like to consider is, well, I would start first with some assumptions. I will assume that there is a linear relationship between the centrifugal forces and the measured amplitudes of the displacement. So everything is linear, or at least behaves linearly. This is the assumption. Even if we have some kind of parameter excitation, the system still was linear. We linearized it at one point, but for the other terms it was perfectly linear. So then we have 2 planes, or I could say 4 planes, 2 planes on each side. One plane, or in total 2 planes, in which we measure the displacements, so where the bearing is, and then we have the 2 balancing planes. And in these planes we can represent the centrifugal forces, U1 and U2, by complex numbers, by a complex pointer, and also x sub 1 and x sub 2 here, so the displacements, by a complex pointer. You can see that this complex pointer is represented by this exponential function, telling you that, well, there's the classical rotation, but that these are really complex numbers because there could be a phase shift. For example, due to some first order terms, to some damping terms included here. Now, as I assumed the linear relationship between the displacements on the one side and the forces that are needed to be created by the masses, additional masses on the other side, I represent that linear relationship by a matrix. by a matrix with coefficients, and these coefficients, they look like, so from the notation, like the influence coefficients, and what they are also kind of influence coefficients between displacements and forces. So classical concept of influence coefficients, but they can be complex numbers. So the influence coefficients in general could be complex numbers due to the fact that we could have some first order terms in the equations of motion. And now the question is, well, if we want to relate the displacements to the forces, we have to know that matrix here. Then it's easy. You just have to invert that matrix and you get the forces. But how can we compute that matrix if we just do these measurements here? Well, you can't if you don't do some kind of special measurements. You can't do it in one run. So when we need 2 calibration runs with calibrated masses, so we add some mass and then we do the measurements and we compute the appropriate influence coefficients, and we repeat that experiment with the second mass and do the and compute the influence coefficients from measuring the displacements, and then we know that matrix, and then we can finally do a third one. This is the basic idea. So without any calibration, without 2 calibration runs, you cannot compute that matrix or determine that matrix. Well, you could do it theoretically, but you would never finish it. So therefore, 2 calibration runs are necessary before we can determine the forces that act on our real system. So how is that done? Well, let me move to the case of series balancing. Suppose you have one rotor supported in these bearings, and that rotor is the perfect rotor of your choice. And you have a series production of other rotors, and you would like all the other rotors to look like that perfect rotor. So we start with a perfectly balanced rotor, and we do the calibration runs on the perfectly balanced rotor. So we add some additional masses, and then at the very end, after the calibration runs, we determine here the forces that we have to then balance in the balancing planes. So let's start here. We have our representation of the displacements as complex numbers and the forces as complex numbers. The first calibration run is done with an imbalance at M1 that we add to the system, that we add in the first balancing plane at a certain location, namely at 0 degrees, whatever the degrees you mark your system. You measure the angle here. So our representation of the force is then just by a real number u sub 1, m sub 1 r sub 1 omega squared, and 0 in the second entry, because the second entry refers to the second balancing plane and there is no entrance. And for the first entrance, there is just for the first part here, for one head, there is just one real number because of the choice of that angle here. There is just a real number, the imaginary part is 0. You start to measure to determine x1 hat and x2 hat, and now it's quite simple to have that equation, namely it's just alpha 1 1 u sub 1 and alpha 2 1 u sub 2 u sub 1, sorry. So you divide by u sub 1 and you obtain the 2 influence coefficient alpha sub 1 1 and alpha sub 2 1. You do the same with the second calibration one. That is no additional mass on the first balancing plane, therefore the 0 here. In the second balancing plane, you add a mass, you choose the angle to be equal to 0 here, so that you can represent it here by a real number. You switch on your rotor so that it rotates in stationary state with omega. You do your measurement and you compute, you obtain x1 hat and x2 hat. You divide by u2 and you have alpha 1, 2 and alpha 2, 2. Having now the whole influence matrix of influence coefficients, you again do the measurement. Now, not with your perfect rotor as before, but with some imperfect rotor that you want to balance and that should look the same as that rotor. So you know the influence coefficient for that perfect rotor. You switch on the engine, you do the measurements, you determine x1 hat and x2 hat for your non-perfect rotor. You invert the matrix of the influence coefficients. You get the forces u sub 1 and u sub 2. Now the question is, what should I do if I don't have such an ideal rotor? So for example, if I drive in a workshop with my car and ask the guy to balance my axle, he won't come up with the matrix of influence coefficients for my car. So there should be something different possible, right? Well, think where we need that ideal rotor. We need it for the calibration runs. The calibration runs are so if I would add this mass, they are composed that I add a mass point to that, so a well-defined mass point to that ideal rotor. What would happen if I add that mass point to my non-ideal rotor? Well, the problem is I can't separate the effect. What is the effect of the misbalanced or imbalanced rotor, and what is the effect of the imbalanced rotor by that additional mass, right? But what I can do with my measurements is I can measure with just the unbalanced rotor. Then in my system, measurement system, so electricity, again, mechatronic machine that we exclude here, I can set these displacements artificially to 0, add or plug in my additional mass and obtain just the effect of that additional mass. So it's just a question of how you do the measurements. Yeah? So this is shown on the next slide. So if you balance without an ideal rotor, you start your measurements with the unbalanced rotor, you adjust these results that you obtain to 0 in your system, store them in your system and take the difference, and you have an ideal rotor. And so you can continue with 2 calibration runs and with the final measurement runs where you switch off or take away these additional masses, of course, and where you switch off these taking these differences or taking this adjustment to 0 here. Yeah. And that's all I would like to tell you for the rigid rotor. Just one remark, where there is, of course, a lot of technical information available on how to carry out balancing in practice. In practice, of course, it's never possible to exactly balance a rotor. Yeah? So you need some kind of residual imbalance that is allowed. And that you can find in classical standards. So in the DIN standard ISO 1940, the admissible residual imbalance values are shown. They are, of course, dependent on not only on omega, but one can imagine that depends on omega, but also on E. Yeah? So if your E is larger, you must have a lower omega to have the same effect, to have the same imbalance in terms of residual forces. Then for higher values of omega, there you need a low value of E, yeah? Leading to the same residual forces. That appears to be quite clear. And the last question then is, what happens now for an elastic rotor? So what is the difference if we do not have a rigid rotor, but if we have, for example, a Jeffcott rotor or even a multi-disc rotor. Well, what you lose here is the independence of the balancing state from omega, because your shaft deforms. The rotor itself will deform. So depending on omega, it will be in different states of displacement, corresponding, for example, to different modes, vibration modes. You know that for each eigenfrequency, you also have an eigenvector, and that eigenvector corresponds to the shape, to the deformed shape of a flexible system. And therefore, the balance state depends on omega. So as there are n natural frequencies, we will have also n balance or 2n balancing planes here. This situation is shown in these diagrams. Well, if you look at that diagram, suppose you have some kind of force F0. You add in the two balancing planes the mass points m sub 1 and m sub 2, leading to forces F sub 1 and F sub 2. Now, if you cycle through the different states, so if you increase omega, then you will find here the first mode shape of a bending beam, like this. You will find the second mode shape, and you will find a third mode shape. And what you can see is that, well, you thought perhaps I want to balance this state here. And, well, I put my balancing planes close to the bearings because I know that the displacement there is quite small in that first vibration mode. But if you then operate your rotor close to the third vibration mode, to this one here, then you see that, oh, the situation could become dangerous for this mode, because the forces and the balancing masses, they act at a position where you have the maximum displacement in this mode. So it will start to increase that displacement, and oh, suddenly you hit something there, the surrounding or whatsoever. So, or you create displacements that are too large, that are unacceptably large, and stresses that are unacceptably large, and there could be some kind of damage there. So that's very important, that due to the fact that we have to balance each state separately and we have two unbalancing planes, there is an influence or an interaction between the balancing weights. They can also cancel each other, the effect. So that makes the balancing of flexible rotors so difficult. Usually you want to balance them only in the range of operation, and vanishing bearing forces is not the same as vanishing rotor displacements. I should add here. And finally, also for this case, there are tolerances for admissible imbalances, and they can be found in the ISO standard 11342. And the fact that the vanishing bearing forces are not related to vanishing rotor displacements can be seen here from this figure. If you add these additional masses due to the flexibility of the shaft, you will see, of course, displacements, because they are related to the flexibility of the shaft and not necessarily to the vanishing of the bearing forces. Well, this is the end not only of my presentation here on the balancing of elastic rotors, on this nice displacement measuring balancing machine, but it's also the end of the whole chapter on balancing of rigid and elastic rotor. In the next chapter, I would like to move away from these rotor systems and discuss with you drivetrains, another important component in machines. And we will discuss then torsional vibrations that often occur in drivetrains. So if you're interested in torsional vibrations, watch the next video. Thank you very much for your attention.